Hey everybody, Mr. Judson here. I want to try and do something that's new for me. I'm not sure I'm really comfortable with it, but I just think it needs to happen. I want to do a Teams meeting on Wednesday at 11 o'clock for anybody that's still thinking about Central Washington. I know I sent out the information email and I also did a video, but I'm getting lots of questions coming back. And so I just want to give you guys an opportunity to ask those questions. And so we'll just do it through a Teams meeting. I'm not very good at this. I've only done Teams 4 times now. I actually did do my own meeting once with the math department, and so I'll get better as time goes, but I just think I need to do it, and that way we can be there to ask questions, and I'll get them answered for you guys. So Wednesday at 11 o'clock is when we'll do this. And you know, for those of you who are crying that I don't get out of bed till 2, well, this one day you can get up a little earlier. All right, so today we're moving on to section 3 in chapter 6, and I want to take a look at this one problem right here. Our book doesn't have a whole lot of those. Let me just cover up the solution for a second. Let me zoom in. All right, so there we go. If you have your book, you know, you could turn to page 425. It's example 7. Maybe just cover up the solution so you don't see it right away. And what we're talking about here is a wildlife population. It has to do with coyotes. And it says that the rate of change of the number of coyotes, N of t, in a population is directly proportional to 650 minus N of t, where t is the time in years. When t equals 0, the population is 300, and when t equals 2, the population is increased to 500. Find the population when t equals 3. So the first thing we have to do is we have to come up with an equation using some calculus. And so we want to write down the differential equation that we have to solve. And so let's start with that. You guys write down the differential. I'll pause for a second and then I'll come back and do the same thing. Alright, so this is on page 425, example 7. So it starts off, they say that the rate of change of the number of coyotes, so that would be, it's a rate of change, so n prime, or dn over dt. That's how the number of coyotes is changing over time. So the rate of change of the number of coyotes in a population is directly proportional, so I'm going to do k times something, directly proportional to 650 minus n of t, which I'll just write down n. And there it is. That's the differential that needs to be solved. So now you guys go ahead and take that and see if you can solve it. Alright, so I need to start with my separation of variable. So the dt has to go over on this side. This set of parentheses here that has an n in it has to come over to this side. So if I bring this over and divide, I have 1 over 650 minus n dn is equal to k times dt. And so now I need to integrate both sides. So I'll do the integral of this and the integral of this. To get a u prime over u, the derivative of this is going to be -1. So I need to put a negative sign there and then a negative out in front. And so now what I have is a negative natural log absolute value of 650 minus n plus c, but again I'm going to add that over here. On this side I get kt plus c. And so I think what I'll do is, right away to get rid of that negative sign, I'll go ahead and move this to the other side and multiply everything here by a negative. So this will be a natural log absolute value of 650 minus n equals a negative kt. When you multiply this by a negative, c could be a positive or negative number, so we'll just leave it as plus c. Okay? All right, and so now I need to, what was that big word we used? Exponentiate both sides. And also, in a situation like this, what we're saying is 650 is the maximum size that this population can grow to. And in the wildlife world, that would be, due to whatever coyotes prey on, there's not enough food to sustain a population higher. When we say n has to be less than 650, that keeps this as a positive number. So when I exponentiate this, I get e raised to the natural log of 650 minus n equals e to the negative kt plus c, which we know this just equals 650 minus n, which is equal to e to the negative kt times e to the c, which means 650 minus n is equal to c times e raised to the negative kt. And I still have to solve for n. So what I'm going to do is I'm going to move n over to this side, make it positive, and over here I've got 650 minus c times e to the negative kt. And I suppose if we want, because this is a negative exponent, I could drop it down below the fraction bar, but I'll just leave it like this for the time being. All right, so now again, to see the problem, if you guys have your book, just open up to that page, 425, example 7. What they told us at the beginning is when t equals 0, the population was 300. So when t equals 0, n equals 300 coyotes. And when t equals 2, the population had increased to 500. So when t equals 2, population was 500. So now I've got to use that information to try and continue on with this problem. So when t equals 0, so if I put a 0 right here, I get an exponent of 0, which means e to the 0 is 1, so I just have c. So 650 minus c is equal to 300. And so that must mean c equals 650 minus 300, and so that's 350. So if you think about the PERT formula, this is usually an initial amount. They set at t equals 0, so whenever we started paying attention, initially we had 300 coyotes, but in this formula, that c value is going to be 350. Okay, so it's not the initial amount here. So here's what we know now. We know that n equals 650 minus 350 times e raised to the negative kt. Our ultimate goal here is we're trying to answer the question, what's the population when t equals 3? So I can't just plug a 3 in yet. I still need to know what the k value is. So when t equals 2, our population was 500. So 500 equals 650 minus 350 times e raised to the negative 2k. And so now I need to solve that equation. So I'll bring the 650 over here and subtract it. That would be a negative 150. equals a negative 350 e to the negative 2k. Then we'll bring that negative 350 over here and divide. So that'll be a negative over a negative. It's positive. 150 over 350, I can get rid of the zeros and call it 15 over 35. And divide by 5, that would be 3/7 is what that would reduce down to. E to the negative 2k. So we're trying to solve for a variable that's in the exponent, so that means I want to take the natural log of both sides. So the natural log of 3/7 equals natural log of e raised to the negative 2k. So I'll bring that negative 2k down in front, and I get natural log of 3/7 equals a negative 2k, and then natural log of e is just 1. So to solve for k, I just have to divide by negative 2. Alright, so I got natural log of 3/7, 3 divided by 7, divided by a negative 2. And so what I got here is k equals 0.424. And I'll keep track of the exact value in the calculator so I can, finish up the last part to this question. Now what I have is n equals 650, I'm going back up to this equation right here, minus 350 times e raised to the negative 0.424 t. So there's my final equation. Now the last thing I have to answer here is what was the population when t equals 3? So I just have to go back and plug that in. So let me just erase this. And at this point I'm going to say n of 3 is equal to 650 minus 350 times e to the negative 0.424 times 3. And so I'll put that in the calculator. I'm still going to keep track of the exact value for this. So 650 minus 350 times e raised to the, go up here and choose the last answer, times 3. Okay, so I had to be careful of one thing. When I put this into the calculator, I got a negative 597.47 coyotes. You can't have a negative number of coyotes. When I went and did the last answer, I hadn't put that negative sign in, and so that threw it off. So make sure you get that negative sign in there. And when you do that, you end up with 551.802, which we'll just call that 552 coyotes. There's our answer. Alright, so the rest of section 3 is just more questions where we're trying to solve the differential. So let's go ahead and solve this one. Alright, so let's see, if I move everything to the other side, this right here will become dy over dx. I've got a natural log of x squared. This still has a 2x here. So I'll have to go ahead and divide by that because I want to get all the x stuff on one side, y stuff on the other. So dy is going to equal natural log of x squared over 2x. This dx here I'm dividing by, so when I move it over here I would multiply. So there's our separation of variable. Now we need to integrate both sides. So I'll integrate each of these, and what I get here is just y. Yeah, what am I going to do with this? If I do a substitution, if I say let's let u equal natural log of x squared, then du would equal u prime over u. So that would be 2x over x squared. And I just took the derivative of x, which if I cancel an x with an x, I would get 2 over x dx. So according to this, what I have is natural log of x squared. That's going to be my u value. I've got 1 over 2x here. I don't really want a 2 in the denominator, so what I'm going to do is I'm going to go ahead and move this outside the integral, this 2. We'll just move it out here. And now what I have is an x value, dx. Still don't quite have everything I need. What I need to see is 2 over x. So I'm going to multiply this by 2, which means I need to divide on the outside by 2. And so now this thing will become y equals 1/4 the integral of u du. So just a good old-fashioned substitution problem. And so that means y is going to equal 1/4. When I integrate this, I would get u squared over 2 plus c. When I distribute that 1/4, again, this will still be c. So what I'm going to have is u squared over 8. And so u is the natural log of x squared. I've got to square that whole thing over 8 plus c. There's my solution to the differential. You can't bring this 2 down in front and simplify farther because that 2 is not part of what we're taking the natural log of. I could bring this 2 down in front. Actually, that might be a good idea. If I did that, I would have 2 natural log of x squared over 8. If I square the 2 plus c, if I square the 2, what I get is 4 natural log of x squared over 8 plus c, and then that 4/8 can reduce down to 1/2. So I guess we could say that y is equal to 1/2 the natural log of x squared plus c. That might be the answer they have in the back of the book. All right, let's try another one. All right, you guys go ahead and try this one. All right, so we need to go through separation of variable first. So let me just write this as dy over dx times x squared plus 4. Over here I still have xy. And so what I want to do is move this over and divide. So I'm going to have x over x squared plus 4. I'll move the dx over and multiply. And then the y needs to come back over to this side, and we're dividing by that. So 1 over y dy. So there's my separation of variable. Now I'll go ahead and integrate both sides. And so what I get here is u prime over u, so this would be a natural log absolute value of y plus c. This over here is also a u prime over u. So let's see, that would be, the derivative of this would be 2x, so I need to see a 2 there, so I'll have a 1/2 out in front. And so what I get is 1/2 natural log absolute value of x squared plus 4 plus c. So when I exponentiate both sides, it would look like this. I would have e raised to the natural log absolute value of y. That equals e raised to the 1/2 times natural log absolute value of x squared plus 4, which this is always going to be positive, so really we don't need the absolute value signs there, and then plus c. So I think what I would do next is I'm going to bring this 1/2 up here, so I've got e times the natural log of the square root of x squared plus 4, right? I've got a log, so I can bring this back up and call it the exponent, so I've got 4x, or x squared plus 4 to the 1/2, which is a square root, times e to the c. And so over here we still have, I guess this will just become y. I'm just going to make a little note out here. I want y to be greater than 0, so I'm not taking the natural log of a negative number. I think by the time when I look at this, this has to be a positive number no matter what. E raised to a positive number is positive. This is positive no matter what, so y has to be a positive number. Alright, so now what I have is y equals, this is just a constant c, times, this is just going to be the square root of x squared plus 4. And there I have solved that differential. Alright, so that's it. Nothing new, more of the same, maybe pushing the ideas a little bit farther. I would say as far as key ideas go, probably that coyote problem, that's a pretty important concept right there, is trying to take a population problem and change it to a differential and doing some calculus to work your way through that. So I believe we're now on number C9. This is on page 429, and we're going to do 15 to 23 odd and 53 and 54. So one quick piece of information. Don't forget Teams meeting Monday or Wednesday at 11. We'll talk about Central Washington credit. If you're not signed up for Central Washington, there's really no reason to be part of that. Also, I'm going to try and do some office hours. I need to do a little work on this first, but just to give you guys a chance to ask questions if there's something you got stuck on. We really don't have that unless you send me an email, which a few people have, but not very many. So I'm going to do something called office hours. It's something that your teachers do in college, and it'll be an hour where I just make myself available through Teams. I'll send everybody out an invite. If you don't have any questions, don't worry about it. You don't have to be there. But if you do, then you can jump on during that hour and just say, hey, Judson, are you there? And I'll say, yes, here I am. And then you can, if you have questions, you can go ahead and ask that. And I think that'll be a helpful thing. I'm not sure exactly what time I'm going to do those. Maybe I'll decide by our Central Washington meeting on Wednesday, and I'll let you guys know that. All right, that's it for today. You guys take care, stay safe, and I'll see you next time.